So thank you very much for the opportunity. So I just wanted to take the first couple of slides just to talk through GenderMark and a little bit about who we are. So we are a machine builder. We design and build production lines that assemble predominantly automotive components. We're a team of about 800 people with 2 factories, one in South Africa, based in PE, and another one in India with sales and service offices in Europe and the US. This is an example of one of the machines I'm most proud of. Reason being is it is VW's first lights out catalytic converter assembly line, building catalytic converters in Germany. Designed and built in South Africa, sent to Germany. I often tease our German colleagues with the fact that they say that you cannot buy technology from Africa, yet here it is. And they bought it twice. Makes me even happier. The next slide I wanted to share with you was just to give you an idea of the other types of production lines we do. This is a differential assembly line that assembles differential. Cycle time is about 48 seconds, and this is a time lapse of us putting the line together on our shop floor in PE over an 8-month period. So this is what we design, manufacture, assemble, commission. We would run about 200 components on our shop floor, pack it up. I think this was like 15 or 16 containers, sent over to the US, and customer uses our product to build their product at the end of the day. And the last one I'd like to share with you is really around, obviously there's a big hype around electric vehicles, and through our Indian business, probably 60% of our turnover at our Indian business is all related to electric vehicle component assembly. So this is an example of a cell sorting line. So this takes cylindrical cells, basically 6,000 cells an hour, sorts them and puts them into modules, laser welding the tabs on, that eventually find their way into vehicles in India. So this is a fully automated production line. We obviously have the other extreme of completely manual assembly lines. So that's a little snapshot of who we are as a company, and the rest of my talk comes from this perspective. So we start literally at the ground, at the factory, and we build up the factory. We don't come from an IT perspective, from an ERP down, just to add to the acronyms of the day. So I've got a couple of questions. I think they told us a long time ago that data is the new gold. I'm pretty sure those of you that have factories are collecting tons and tons of data. So technically, you should be all gazillionaires by now, right? So the question is, why are we not gazillionaires yet we've got lots of data if it's the new gold? Second question is, this is an inaccurate slide. Industry 4.0 was announced at the Hanover MESA 12 years ago. Has it been a revolution? The iPhone is 15 years old. That has been a revolution. So something almost as old as the iPhone, Industry 4.0, has it really had the impact that we expected? And the question is why? It has had an impact, no question about that, but has it been the revolution that everyone talks about? I would argue it hasn't. And my thesis today is why I think that is the case. And this is the picture that describes it all, a picture from generative AI. I believe that solutions on the market today are basically a golden roof on a shack. So you have a production facility, and you put a bunch of data collection on top of that, and you expect a revolution, when actually the problems are at the foundation of your production facility. So I think that we need to change the way we view the way we adopt technology in our factories and actually focus on what I call the foundation. The problem with that is that nobody pays for that. That is the unsexy part that everyone leaves to the engineers on the ground. There's no business case that says, let me sort out my protocols in my factory. There's no business case that says, do I use MQTT? Do I use OPC? Nobody pays for that. They only want to pay for the golden roof. So people focus on delivering the golden roof without understanding the foundations of what makes a production facility. So I would argue that we need these software-defined solutions. And I want to talk about 2 examples of software-defined solutions. First one is this picture. Who had a BlackBerry? Age given away. It was a trick question. But this is Steve Jobs announcing the new iPhone. And we know what happened since then. And basically what the BlackBerry was a static piece of hardware with a piece of firmware that worked in a certain way. and that was it. If you wanted a new feature, you buy a new phone, right? What Steve Jobs introduced was a software-defined product. So he created a static piece of hardware. They spent a lot of effort developing an operating system that allowed other solutions to be adopted on top of that operating system. We call them apps today, that allowed you to change the functionality of your phone. Anyone with the iPhone 15? 14? Oh, come on, guys. 14? Your two phones are not the same. Impossible for your two phones to be the same. Your phone has been customized to what you want. So that by standardizing the hardware, they still created that flexibility and adaptability of the product, software-defined products. That allowed new functions to happen on the smartphone. The second one that's rocking the world. And not because it's an EV, I would argue, because there's many other EV vehicles on the road today. VW ID4 was meant to be a challenger. Why? Because it's 30% more expensive to produce a VW ID3 than a Tesla. What Tesla have done is two very important things. They've changed the physical structure of the vehicle using the gigapress. So it now takes 3 huge presses to produce the underpanel, whereas VW need 100 robots to do that. So it takes 30% less time to produce a Tesla than what it does a VW ID4. And secondly, most importantly, is they've changed the way the vehicle is defined. So they have a software-defined vehicle. So this picture over here, I'll use the pointer on this side, is the conventional electrical architecture of a normal vehicle. What you see is a set of fixed boxes, ESP, ABS, lighting controller, infotainment system. They're individual pieces of hardware, software that do certain functions. What Tesla has adopted is a mainframe. So you have a mainframe in the center that controls everything, and then you have a distributed solution. What that means is that Tesla can change. Oh, and the second most important point is that these boxes are not owned by VW. The software is owned by Bosch and all of the suppliers. The headlights are owned by Hella. So VW can't change the software on the lights or ABS because it's locked in by the physical product. Whereas with Tesla, they have a software-defined vehicle with a mainframe, so they can, if you want to double tap the button on your boot and flash the lights, they can do that. That's why you can order heating online in your Tesla. They've standardized the hardware in the vehicle, and you can then change the features on the vehicle. So that's what Tesla have done. And so they've been able to reduce the number of physical variants, change the way it mechanically produce the vehicle, and they can make it cheaper and cheaper, yet the vehicle is completely customizable like a BMW X3 or X5. So what can we learn from this idea of a software-defined product? And what we've learned over the last couple of years building thousands of machines for our customers is that maybe we need to define it a little bit differently. Maybe when we design a production line, we should start with the digital infrastructure first, and then define what the production line does afterwards. Get the architecture right first, then define the rest of it. So the next couple of slides are really kind of talk to that point. So the first thing I think the architecture needs is a brain. Earlier there was a talk about unified namespace. This could be a similar concept. The production line first needs a brain and a data structure. We then need an infrastructure. So how am I going to communicate to the different machines on my production line? These little arrows are the key to it all, the communication protocol to the different machines. This is the part that's unsexy, that nobody wants to talk about. MQTT could be an option. OPC UA, not my favorite option, but an option. There are other options out there. So once you've got that, you can then start adding your machines onto your production line. And I think that this is what all organizations that produce something should do first. Then you can tell the vendors of machine A, B, C, D how they must develop their machine to fit into your architecture, as opposed to the vendor telling you what the architecture is. The next step is what do we put into the brain? So things like bill of materials, bill of process, all of that kind of stuff, work instructions for operators. We can then build, once we've got the brain with all the information, we can then build the actual equipment. Send the machine parameters, work instructions, whatever it is, to the actual equipment from multiple vendors. I think earlier there was a concept that was discussed about just plug and play vendors. This is the future, I think, of where you could have plug and play vendors. And then earlier there was a lot of talk about contextualized data. If I know what I need to build, I know how I built it, and then I have contextualized data that confirms what I did. So now I don't need to have manipulation of data to add context. I have contextualized data right from the beginning. And I think this is the foundation that must be put in place before you put on your golden roof. So then we can start building the trusses of the roof. One example is a live production line that we built for one of our customers. So this is a station. The product comes into the station, and depending on the product in the station completely is reconfigured. So every product that comes through the station, there's mechanical limitations, obviously. It changes based on the product, based on what sequence must be followed. So this is an example of where we've created a software-defined solution based on the product that's in the station. It's not a fixed hard-coded PLC that does a fixed sequence. It changes based on the product in the station. The next one is about rework, but I'm going to skip that for the sake of time. And then we can move to data analytics. So I haven't even gotten to the AI topic yet. And I think you can't get to AI topic. I think that was spoken about earlier. Until you actually have all of the data structures, contextualized data, and some examples of data analytics we provide our customers is this is a bar chart of cycle time with all the stations on the horizontal bar and the height of the bar representing the cycle time. Each color represents the individual operation in that station. So we now have contextualized data that can become useful. And more importantly, I think the idea of using, this is statistical analysis before you use AI. I 100% agree with that. So this is basically a CPK or standard deviation calculation on cycle time of, I think this line has 500 operations on it. And what we do is we bring to the surface the operations that are the most unstable. So basically what I'm saying over here is oil plug confirmation is varying by 28 seconds, live. So it means an industrial engineer's job, this is their to-do list for the day. Clear these things out. Why are these operations varying? And I think this is far more important than trying to get to AI. And the reason why we're able to do that is we have the architecture at the bottom, we have the communication protocol, and we collect contextualized data from the beginning. This chart is very easy to put together once you have the context. Anyone understand CPK? So measurement of quality measure. So here, this production line again has more than 1,500 measurements that are streaming in live. So we do a live CPK analysis, again staying away from AI, on all of the streaming data coming in, and then we produce the worst parts in terms of quality at the top, processes on top. Then a quality engineer comes to work, they look at the top 10, they can click on the one, and then they can get a live report, statistical report on that operation as it's running on the line. So basically what we're doing is we're creating a to-do list for the quality engineer based off the data we've collected. And then my favorite report is this one. So this is a report that is being widely adopted by operators. So every operator at a screen can hit the My Data button on it, and this is the dashboard that they see. This is Mr. J. Goliath. He's number 4 in number of parts produced on this line. So we're gamifying it. And this creates a level of competition amongst the operators. It's a fun thing to do. But more importantly, on the charts on my far left, I'll zoom into those, we're showing the operator on top which operations they're getting faster and faster at, and which operations are getting slower and slower. And the most interesting thing about this is we now have operators shouting at maintenance. This particular one was a maintenance issue, nothing to do with the operator performance. So we now have a bottom-up driving of improvement within the factory. The second interesting thing that came out of it is they crashed the servers because they keep hitting the refresh button. So on this particular line in South Africa, in PE, we actually had to install a new server to cater for all the queries the operators are performing. So operators are not querying data. And I think this is the idea of adoption that I think is very important, is that we have to understand where the operator is, not try and take the operator to where they should be, and develop solutions from where they are. So that's a little bit about the data analytics. I just want to quickly touch on AI. So I think there are practical use cases of AI. and I'll share some of them with you. Skip through some of these, but this is basically the summary of what I'm going to talk about: computer vision, using data, and then I'll skip generative AI for time purposes. So this is a station at ZF, builds the BMW X3. So we built the whole production line. What we did was we added 4 webcams, 800 Rand, $30, $40 for you, Anand, unfortunately. An NVIDIA graphics card, I think that's like 25,000 Rand, more or less. And we then created some machine learning models using the computer vision elements. What were we able to achieve? This is the first one. What's really critical in this process is the sequence in which we tighten bolts on the axle. You cannot tighten it like your wheel bolt in a circle. There's a certain sequence you must tighten to get the dynamics of the vehicle right. So here we have a machine learning model that detects the position of the bolting tool, and only when it's in the right position do we enable it. So the operator cannot make a mistake. Again, to the point of starting where the operator is, not where they should be. So technology is enabling the operator. We reduce the skills required to actually perform the task, not increase the skills. The next one is this idea of software-defined products. So now I have the hardware in the station. What else can I do with it? So one of the things that they were concerned about was the fitment of this link arm, this banana shape. It could be the other way around, and that's not right. Using computer vision, we now added that virtual sensor into the system with no extra hardware. So just by changing the software, some machine learning, we changed the complete behavior of the production line. Here's another one. These are all add-ons by just changing the software. Determining the orientation of this pallet, because I need to know left and right. I now have computer vision that detects that kip lock, and now I know the orientation of the pallet. Purely changing software by virtualizing sensors, essentially. I'll skip the next ones for time's sake. This is just a little simulation or a video showing what it looks like with the computer vision and the operator guidance together. So on the top you see the operator, the computer vision checking that the operator is picking the right components from the right bin, and then the interface changes. So it becomes the Google Maps for the operator. And based on what the operator does, the map changes. So if they make a wrong turn or make a mistake, the pictures change. So we can now guide the operator even to do a rework in the station if necessary. And the computer vision has actually detected that. So again, to the point of using technology to enable operators, not disable the operators. Let's talk a little bit about data. I'll give you one example. So this is a bearing press, one of the machines we produced. Typically what happens is we monitor the force and displacement, and we create these red limits, the windows, that this graph must go through in order to produce a good part. What we did was we took 156 charts, graphs that we produced off this production line, created a machine learning model, and to not get into the weeds of it, we produced the ideal press curve in red. And you'll see, not so easily, but behind there is a blue curve of an actual press curve. So what we did was we now can do a comparison between the red and the blue curve, and the difference tells me the deviation. One very important point is that you see all these curves have passed. So within the statistical limits that have been set, none of them have failed. So what are we able to achieve? Now I can start to see bigger deviations and even bigger deviations, and I can set a threshold to what I would determine as an error, basically area between the two curves. And what we then realized, when we started to get 10 to 12 anomalies in a row with a certain threshold, we realized that the machining center on the other end of the plant that's machining the housing of the where the bearing goes in is actually starting to wear out. So we can now predict very simply that the tools need to be changed on the CNC machines by just detecting the anomaly, not waiting for the failure. Just an example to your point about where it can be used in conjunction with the statistical analysis. A gauging machine that measures a differential. There was a burn, one of the differentials bumped the gauge sensor, and the measure started to deviate. So just to give you some context here, this is 50 microns, so it's tiny. But that calculation, that value is used in the calculation later down the line, and then we started failing parts. It took them 4 hours to figure out what was going on because everything was passing, it was still within range, but the values were wrong. A simple anomaly detector, in retrospect, would have been able to detect that and at least earlier on give a warning to say, listen, something's deviated from what is deemed as normal, because it's still within limits. The last example I want to share with you is really around prescriptive AI. So this for me is the holy grail, and this is the part that the conclusion of this is that we haven't yet got this perfect, but this is what we're working towards. So the problem over here is a differential, and the idea, the whole goal of a differential assembly line at the end of the day is to select the thickness of these two red shims that is used to set the backlash of the two gears. Ultimately, that's what we're trying to do. To do that, we have all of these measurements. You see all the letters are different measurements that we take through the assembly process, and we do a calculation using this formula, and it never works. We fail every single part. And as true engineers, to fix that, we put an offset. And to make it even more accurate, what we do is we have the operators change the offset every shift. And that's how it's done around the world. This is not a unique South African problem. So based on intuition, the operators look at the results and the trend of the results. They go and manually change K1, K2. And we get basically an 80%, some of the best lines are at 80% first time through. So built into almost every single differential line is a rework loop. So you plan for that 20% because you know that it's going to happen. Interestingly, our customer asked a third-party company called Acerta, a US-based company, to do a reinforced learning model on the same process to help predict K1, K2. Not the actual shim thickness, but the K1, K2. And they actually managed to up it to 90%. Still not perfect, and it took a lot of money, a lot of effort to get it to 90%, but at least it is an improvement. And I think the continuous learning of this process with the right feedback is the right approach. But we try to target 100%. But a 10% improvement is significant in that factory. So let me try and summarize here. So what we've been able to do is close the loop. So we're able to do some predictions, as I showed you, and most importantly, feed that back to the brain. And the reason why that's important is because if I predict something and I can't effect the change, what's the point? You have to be able to go back into the data model and change settings, either with human intervention to confirm, or at the end of the day, when we trust the system, to automatically, dynamically change the production line. And what we've built is an autonomous system. We close the loop. And you can only close the loop if you have the foundation right. Golden roofs don't close the loop. And then to add to that, our vision is to be able to add on third-party applications that can talk to this data model and manipulate the information, very much like the App Store. So imagine the App Store for your production line. So if you have the right data model, you can, or unified namespace as what was discussed earlier, you can bring on different vendors to manipulate your production line's behavior. So in conclusion, this is my last slide. I think what a lot of MES systems do is they measure when you get burnt. They measure very static outcomes. What's important in the future is to measure the warm data in between, because what prevents you from getting burnt is the feeling of it getting warm. And nobody measures that feeling so that you can train the brain with the warm feeling. All the data we give systems today are just the outcome, the result. Where do you get the warm data from? And that's why I think you have to get the data infrastructure right first, so you can get the warm data, and maybe one day we can get a real advantage with AI. Thank you.